Hello and welcome to the video series on the signals and systems. So in this video we will be taking on some elementary signals that we use a lot in signals and systems. Fine. We'll be defining some basic elementary signals and we will see what are their properties, how are they graphically represented, what is their continuous time and discrete time version. And then later on, when we discuss systems, we may be using some of these signals to characterize a system. Fine. So there are several elementary signals that feature prominently in the study of signals and systems. And we'll start with the discussion on the exponential signals. Fine. Now, an exponential signal, to be more specific, we will be discussing a real valued exponential signal. We will also be discussing a complex valued exponential signal, but that will be in the context of sinusoidal signals. So a real exponential signal in its most general form, so it has a general form. It is a deterministic signal, and mathematically it is represented as x of t is equivalent to b e raised power at, where e is the exponential. So there are some parameters that are involved, and first the parameter is the parameter b. Fine. It is basically the amplitude of this exponential. So this will be amplitude of exponential. Then we have the parameter alpha. Fine. Not alpha, sorry, the parameter a. And it is basically the exponential factor. Fine. Now, when we say that it is a real valued exponential signal, it means both these parameters, both b, which is the amplitude, and a, which appears in the exponentiation operation, they are both real valued. And in complex valued, either b or a or both will be complex valued. We will take that discussion separately. Fine. Now this a, so this a, which is the exponentiation factor, this will determine the nature of this signal. The nature of the exponential signal. Fine. In the sense that if a, this parameter a, has a value less than 0, means it is negative, then we will have a decaying exponential. That is a kind of an exponential signal whose value will be decreasing exponentially with respect to time. So this is a decaying exponential. Fine. And if we have positive values of a, that's a greater than 0, then we'll have a growing exponential. That is an exponential signal which grows, which increases in value as the time passes. Right? So graphically, this is how they are represented. We have the time axis, then we have the amplitude axis, x of t is going to be EAT. Now this will be a decaying exponential, which means for this particular case, a will have a value less than 0. And for the growing exponential, this factor, exponentiation factor, it will have a value greater than 0. Now obviously this is the time domain representation, x of t. We have a, so let me just write it down here, that in discrete time domain, again if we talk about a real exponential signal, it has a slightly different form, and it is represented as First it will be x square brackets n, that is our universal notation for the discrete time signal, that will have an amplitude parameter b, then it will be r to the power n. Fine. Here of course n is an integer value, and additionally this r is equivalent to e raised power alpha. Fine. And n is going to be a discrete parameter, it is going to be an integer value. Now again, the value of r will determine the nature of the exponential. So if we have 0 less than r less than 1, then we're gonna have what's known as this decaying exponential. Fine. And in case we have r greater than 1, then we will have a discrete time growing exponential. Fine. And this will be the case. X of n is going to be r raised power n, where r is e raised power alpha, n being an integer. So this is a typical case where 0 less than r less than 1, and here we have r greater than 1. Fine. So you should represent these, you should remember these differences in the continuous time and the discrete time case. Now this was a real valued exponential signal. Like I said, we can also have an exponential signal which is complex valued in the sense that both these b and a, that is the amplitude factor and the exponentiation factor, one of the parameters, both of the parameters, they may be complex valued. But such kind of complex valued exponential signals we represent in terms of sinusoids. Fine. So before we go there, we will take a second kind of elementary signal, that will be our sinusoidal signals. Fine. Again, it will have a continuous time version and a discrete time version, and again there is a small difference in interpretation. Just like an exponential signal, we had a slightly different form, b e raised power at, and then we had brn. Similarly here we will have a slightly different form and slightly different properties. We'll discuss them. So the continuous time version, so the ct version of a sinusoidal signal and it can be expressed as, it has many forms, but a general form is expressed as that x of t is equivalent to a cos omega t plus phi as a general expression. Again, there are a few quantities involved. A, it is the amplitude of this sinusoidal signal. Then we have omega, which is the angular frequency. And it's measured in the radians per second. And then phi is the phase angle. Again, this is because it's an angle, it's measured in radians. Fine. Now, a sinusoidal signal is an example of a periodic signal when continuous time domain is concerned. So it is you know that from the period property of periodicity, we say that in the continuous time domain, a signal is periodic if it follows this relation. Right? So if I translate this to the general expression we just had for the sinusoidal signal, it will be omega t plus phi. Fine. And if I simply expand it, it will be omega t plus omega capital T plus phi. Okay. Now for this thing to be true, for a cos omega t plus phi to be equivalent to this, we know that because we are familiar with the basic trigonometric relationship. So it means that omega t should be equivalent to 2 pi, right? Because then it will be a cos omega t plus 2 pi plus phi, which is a cos omega t plus phi. And you know it from the basic trigonometry, from the basic relationships, and that the three trigonometric functions share, right? Yeah, in other words, I can say that time period is equivalent to 2 pi by omega. Okay. So to generalize, a sinusoidal signal, this is an example of a periodic signal with a period t is equivalent to 2 pi by omega, where the quantities are defined. T is time period in time in seconds, omega being the angular frequency in radians per second. Fine. Now if I take the discrete time version of this sinusoidal signal, so this was continuous time. If I take the discrete time version, so discrete time version of this sinusoidal signal, it will be typically x of n, where n is a integer or sample point, whatever you like to call it, then a cos. Then we use second notation of omega just to differentiate between the continuous time sinusoidal and the discrete time sinusoidal, omega n plus phi. Now the terms involved, the quantities involved, they have the regular meaning as in the continuous time case, a being the amplitude, omega being the angular frequency, and of course phi being the phase angle. But n is discrete, and that kind of puts a condition on the periodicity of the discrete time sinusoidal signal. Okay. So again, we know from our general relation the condition for periodicity in case of discrete time signal, it is defined by x of n is equivalent to x of n plus capital N. But the thing is that this capital N, it has to be an integer. So again, if I use a similar kind of substitution as I did in the continuous time case, so this left hand side will be simply a cos omega n plus phi, and on the right hand side I will have a cos omega n plus omega capital N plus phi. Fine. But here is a condition. See, you compared this and this and you came up with this kind of a relationship for the signal to be periodic, that omega t is equal to 2 pi. But here on it will be slightly modulated. So in the sense that let me go to the next page. Yeah, just here. Now to ensure to satisfy the condition of periodicity, we have to ensure that this omega n is equivalent to 2 pi small m. Now why this small m, why I am using this modulating factor, is because capital N has to be an integer. Unlike here, t could have been any value. There was no restriction on this. But since we're talking about discrete time case, and for a discrete time case, the time period, the fundamental time period, it has to be number of samples. It has to be an integer value. So to satisfy that condition, I'm using this, which means capital N is equivalent to 2 pi m by omega. Here, of course, small n, capital N, and this small m, they have to be integers. Yeah, integers. Fine. So this puts a condition on periodicity. So unlike continuous time sinusoidal signals, not all the discrete time sinusoidal signals are periodic, and you have to basically come up with the condition, or you have to look up for the condition under which condition my discrete time sinusoidal signal will be periodic. So we'll do a small example in the next video. The next video will start with a small example to further elaborate this difference between the periodicity property shares in continuous time and discrete time case.